Let us look at another example. This example, they're asking us for computing the forces through members F to H, G to H, and G to I. That means that we have to compute the forces through F to H, which is right here, G to H, which is right here, and G to I, which is right here. So evidently, a cut through here will help us. And the good thing about this example is that we're probably going to have more forces than more knowns than equations. Therefore, we have to do moments at points away from the cut, which that's the important concept that we have to learn now. So to begin, we're going to do summation of forces. We always do those three things first, where positive is to the right, vertically up is positive for summation of forces in y, and we usually take the moment with the fixed constraints as our point for a moment. Summation of moments at A equals to 0 and counterclockwise is positive. So in X, let's see what forces we have. We have AX and we have AY. There's nothing else in X because this one is a ruler which is only in Y. So summation of forces in X equals 0 means that AX is equal to 0. So if nothing happens, this is static just by having the structure placed by itself on A. Of course, once you have cars and vibrations and earthquakes, then AX has to be computed, but then that's a different problem. They'll probably give you forces in X, like we've done before. Summation of forces in Y equals to 0. Then we have a bunch here. We have Ly positive minus 1, 2, 3, 5 kilonewtons times 3 forces minus 1, 2, 3, 4, 5, 1 kilonewton times 5 forces equals to 0. Therefore, y equals to 15 kilonewtons plus 5 kilonewtons. Okay, so what? Okay, but hold on, I'm missing something here. It's not that simple because I'm missing ay plus ay equals to 0. There you go. So ay is 15 plus 5 minus ay. Okay, now we got the equation. Yeah, so usually when you do summation of forces in y, you're going to have more than one unknown. That's why we have a third equation, which is summation of moments. And we're going to do it around a, so we cancel a equals to 0. And in this case, each element is 5 meters, and the height is 8 meters. Therefore, what we need to do is, there's no moment, so we start from 0. So we do this, C is going to be counterclockwise. Let's do Ly first. Ly is going to be clockwise, so it's positive. Ly times 30. All right, and everything else is going to be counterclockwise. So it's going to be negative. It's going to be clockwise, I'm sorry. So it's going to be negative. So we have minus. This is going to be a pretty long equation. So we have 1 kilonewton times 25 meters minus 1 times 20. I'm gonna leave the units out, but we know it's kilonewtons to meters. 1 times 25, 20, 15 minus 1 times 10 minus 1 times 5 minus 5 times 5 minus 5 times 10 minus 5 times 15 equals to 0. Okay, so we have that Ly is minus 25 kilonewtons per meter. So all the units are going to be kilonewtons per meter. Minus 20, minus 15, minus 10, minus 5, minus 25, minus 50, minus 75, right? 5 times 15 is 30, 60, 75. Minus 75 is equal to 0. Therefore, Ly is equal to 25 plus 20 plus 15. So if we go all from alpha, 25 plus 20 plus 15 plus 10 plus 5 plus 25 plus 25, and Ly actually is missing 30. All right, plus 50 plus 75. Okay, all that divided by 30 is 15 divided by 2, which is 7.5, correct? 7.5. Okay, so let's do something here to save time. We're gonna do Ly equals plus 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 divided by 30 30 meters, I'm sorry. So everything has meters. We get kilonewtons, and this was 7.5 kilonewtons. Okay, so we got L. Then we can come back to summation forces in Y and do that Ly A is equal to A is equal to Ly minus 15. No, this is not true. A going to the opposite side is equal to 15 kilonewtons plus 5 kilonewtons minus Ly. Okay, so AY is equal to 20 minus 7.5, that's 12.5 kilonewtons. Okay, we got AY and Ly, so this should be the easy part. Now, with those forces, we can go ahead and find the elements FH, GH, and GI. Okay, so we start with some geometrical concerns or some parameters. So if you notice, since we have this cut, we're going to have a force here, either compression or tension. So that force has an angle, obviously, with respect to our horizontal plane, and that angle is the same as this angle, say alpha or theta. So let's find alpha. Alpha, the angle alpha, is, we can do several things. We can find this length, that will be 5, 10, 15, and this is 8. So we can do a hypotenuse and cosine, or we can do tangent. So let's do that. Tangent alpha, since we have the information for tangent, we have the height and the base. Is equals to the y versus the x. The y here is 8, and the x is 15. So when we go to our calculator, we have to do alpha equals tangent inverse of 8 divided by 15, and that's going to be in degrees. So let's go to our calculator and do 8 divided by 15, 0.53. And then we're going to do tangent. I always forget how you write tangent inverse in Wolfram alpha. Is 28.07 because we want degrees, not radians. So this angle alpha is 28 degrees. Okay, we have that. Therefore, we can create our system of forces for this section. Okay, so now I have the system of force, the free body diagram on the screen to help us determine the system of forces for finding the element from 2GH and the element, well, actually they're asking for F, G2H, GI, and GH. So GH, GI, and FH. Okay, so they're not asking for GI. We don't need a cut there. So the cut, which was over here, like so, we'll have the forces right here, because remember that we still have the points F and A and G right here. F and G. Let's see. So it's pretty clear that G is right here and F is over there. Yeah, so we have a point F and J. And G, I'm sorry, F and G. Okay, so next we have to use something to get our the forces that they're asking for. So if you notice, if we do a summation of forces in X is equal to 0, but we have two components in X, F from F to H and G to I, and actually in G to H we have three components but no information, so this is not going to work. Summation of forces in Y is equal to 0, and we have one force that we know, two that we know, J and L, and H is 1 kilonewton, but we don't know the force for F to H, the vertical component, and G to H, the vertical component, because remember that at point H you have, they're telling us that there's a force FH and another one that is F G to H. Okay, so they have two forces, but if you want to find those forces, what we have to do is get the components of the forces, since we don't have any other information. And the component of the forces are so there's F G to H. I don't know which one is bigger between F to H and G to H. F to H, and this is an X, and X, and F to H in Y, F G to H in Y. I don't know which one is bigger, but we know that we have four. In X we have forces but no information. In Y we have two forces and two unknowns in one equation. So, but we do have this angle here, which is alpha 28. Okay, so one thing that we can do is do a moment, and this is the new concept that we're going to learn. So when we have more unknowns than equations, we can actually do a moment. But the important point is where to do the moment. And the moment is at the point after the cut. So we can either do G or F. So if we do G, we cancel FG to I, and then we simply have the components for F to H, and G to H also cancels because it makes it to the point, and the force going to the point will make it 0 in a section. We saw that last time. So this one is 0, this one is 0. The only unknown is F to H. It's not going to G, it's going to F. If we do a moment at F, we could find G to H, G to I. So let's do a moment at G first, because we can find F to H. And at that point, what we have is that is equal to 0. We're going to keep our convention of positive counterclockwise. And we have that 7.5, which is Ly, times 15. Remember, this is in kilonewtons, and this is in meters. And it's giving a positive for momentum. Sorry, a moment. Every single time I say momentum, that's fluid, is moment, not momentum. I apologize. Every video I said momentum is moment. And let's carry on. Minus 1 kilonewton times 10. Don't forget that we'll have 5 meters here, and we don't know this distance. Yes, this distance is at F. At F is 8 meters. In fact, they're giving us this distance right here. But we have the angle, so we can use either or. Next, we have another force, which is the one that we care about, which is F to H. Okay, and F to H has a component, and let's see which one we use. We use F to H in X, right? Yes, let's see. So F to H, this one be, this F to H is giving positive moments counterclockwise. So plus F to H, the force that we are now, times, okay, so this component, so first of all, this angle right here is 28. So let's go back to our point here. For point H, we have force F to H, and then we have that the let's see, the force in X is 28 degrees. So this force in X is F to H times cosine of 28. And that distance to G is 8. Okay, so that's what we need to write down. Times cosine of 28 times 8, and this is equal to 0. Now notice that even though at H we have a component in Y, we don't consider that point. And it's tricky because here at this point called point F, we have the force F to H, and we have the component of F to H in X and F to H in Y. Let me fix that. F2H in Y. So this is 28. This guy is F. Remember the main force, the element force is F2H. So this is the magnitude F2H times cosine of 28. And this is F2H times sine of 28. But if you follow this point, you have point G. Therefore, this distance is 8, but this distance is 0. That is why we don't consider the force in Y for the moment. So really, what we're doing is that we're placing the forces of F to H at F. Okay? F to H, X, F to H, Y. F to H, Y has 0 distance. It's aligned with the axis. We already know that that's not going to contribute to the moment. F to H, the force from F to H does contribute in X because there's a distance of 8 meters. So that force is, again, the angle here, which is 28. So is the magnitude times cosine of 28. So actually, this is a little confusing here because this is really at point F. Let me do it again. This is at point F. F to H. Okay. Component in X, component in Y. All right, so now that we have that, we can find the moment, the force at F to H. So for that, we do F from F to H times cosine of 28 is equal to 10 minus, oh, this is times 8. 8 times force times cosine of 28 is 10 minus 17 plus 15. Wait, not 17, but 7.5 plus 15. All right, 112.5. Okay, so this is equal to 10 minus that, 112.5 is negative 102.20.5, and cosine of 28, 8 times cosine of 28 in degrees is 7.06. Let's say 7. Let's do that again. So this is actually F to H is 102 divided by 7. So 102.5 divided by 7 is 14.6. 14.6. Okay, so that is in kilonewtons. So I want you to notice something. If we did the point at H, let's do here parentheses, maybe with blue. So summation of moment at G, But if we kept the forces at H and not at F, we would have the same thing, except for the moment, the force at Y will have a moment. Okay, so that is going to be equal to 7.5 times 15 minus 10 times 1 plus FH cosine of 28 times 8, and then the force at Y, which is plus, because it's going to be pulling and counterclockwise, F2H times sine of 28 times 5 equals to 0. So if you solve this equation right here, you're going to have, again, 7.5. So this is going to be 7.5 times 15, which was 112.2, right? No, 112.5. 7.5 times 15, yeah, 112.5 minus 10 plus FH cosine of 28 times 8 plus FH sine of 28 plus times 5 equals to 0. Then we can solve for FH. FH times 8 times cosine of 28 plus FH times 5 times sine of 28 is equal to negative 102.5. Alright, so let's do this part. 8 times cosine of 28. 8 times cosine of 28. We did this already, 7.06. So this part is 7. Okay. The units of this is meters. Is 7 meters. Okay. And then sine of 28 times 7 times 5. 5 times sine of 28 is 2.34, so 2.3. So what happens here? We have that F8, this is F2H, times 7 plus 2.3 is equal to negative 102.5. Negative 102.5. Okay, so that means that the force from F to H is equal to negative 102.5 divided by 7 plus 2.3 is 9.3. Okay, so 102.5 divided by 9.3 is 11.02. So if you notice, this one is 11. With it, if you consider that, I'm trying to explain why we want the force here in F and not in H. Because if you consider the force in H, you're computing a resultant force, F2H, that is actually smaller. And as a rule of thumb, you want to over-design so that your components can have a factor of safety. So that is why in the method of sections, we place the forces at the point, we place the moment at the point away from the cut, and we place the resultant forces away from the cut as well. Okay, so that's why we don't consider the force in Y on H, but in F. Okay, after doing that, we can continue because we still have to find 2 more forces, but it's the same concept. So I won't keep this on the notes. When you open the notes, you will see this part. Right, when you see the video lecture, you'll see why you want to keep the force at that point F. All right, so basically we're done computing F to H, and now we want to compute the next one, which is G to H, and for that, it's going to be pretty simple. It's going to be the same thing, but with the new dimensions. Now, let's consider element G to I. So let's bring the same diagram, or the same free body diagram. And now let's do the forces at G to the H to I. So force from G to I. So the first one we're going to do is G to I. So this one should be pretty simple. For this one, we can actually see if we can find the force without doing any complicated equations. Let's see. Let's try forces in x equals 0. That's not going to tell us anything, because first of all, we want to find, even though we want to find G to I, we have one unknown and two unknowns from, well, actually we can do that. Or summation of forces in y equals to 0. G to I is in x, so we don't need that one. But what we can do is, in case we have computed the wrong force, or better yet, in case we have where computation was wrong, we can use a different method to find GI not involving the forces that we found already. So that's a rule of thumb, because if you find sometimes you need to use the forces that you already found, but if you use a different method, then you can compare later if they match. And if there's an error, then you can go back and see what's the error. So what I mean is that in this case, if we want to find the force at G, then we can cancel all the forces from doing a moment in H. So moment at H equals 0, counterclockwise is positive. And the forces that we have at H are pretty simple, are again 7.5 times 10. This is in kilonewtons and this is meters. Then we have minus 1 times 5. And then the force that we care about, because all of these are cancelled. And then minus, because this force will give it a clockwise direction, F G to I, and the distance here. So we know the distance right here at F is 8. So really the only difficult part here, which is not difficult, is just finding what is this distance. And they're telling us it's 5.3, but how you calculate that? Okay, well, it's pretty simple. We know that we have a triangular shape, or a triangle here, that is 15 and 8 from L to G and from F to L. Right, that's the whole triangle. Actually, we already know that angle, which is 28. And now they're asking us to find the height from H to I, which is, well, let's just call it HI for now. And we know that this distance is, this point is I, this point is H, and this distance is 10. Okay, perfect. So what we can do is, in order to find HI, we can do ratio here. Say 8 over HI, that ratio is the same as 15. Sorry, let's do the other way around so we don't have to divide. Let's do HI divided by 8, is equal to 10 divided by 15, so that we have exactly the same format they do. Okay, so what this means is that this is 2 and this is 3. 5 times 2 is 10, 5 times 3 is 15, and then that tells us that hi is equal to 2 over 3 times 8. That is hi, and that is the distance that we need here. 2 over 3 times 8 is equal to 0. So this should be pretty simple now. We just need to find fg2i. So fg2i, which in our case was negative, yeah, because the moment it's at h. Let's take it to the other side and let's do that. 2 over 3 times 8, they're telling us is 5.33, and then that is equal to 7.5 times 10 is 75 minus 5. Okay, so we have that fg2i is equal to 70 divided by 5.33. And the units of this guy are kilonewtons per meter, and this is meter, so we should have a force at the end. 70 divided by 5.3. 70 divided by 5.3. 13.2. So FGI equals 13.2 kilonewtons. Okay, so this one is pretty simple as well. So we have found to F to H and G to I. Now we only have to find G to H, which is not complicated at all. So for element G to H, which is this force, and again, even though the cut is at this point, we're going to place the forces at the point away from the point away from the cut, which is G, because we already showed that if you place it inside, you're going to get a smaller force, and then your structure is not going to have as good factor of safety. So as a rule of thumb, always remember the point away from the cut is where you place your forces if you want to find internal components and resultant forces. So in that case, if G to H is the magnitude, but by finding the angle will help us find the magnitude. So let's find the angle first. Remember, we already saw these many times, but remember that if a triangle, a right triangle, so like if this is 90 degrees, and this is x, a distance or a force, and this is y, then the angle, you have two angles. Let's call this alpha, and let's call this beta. Or actually, let's use the same nomenclature that they have in this picture. So, okay, let's call this alpha, and let's call this beta. So if you want to find beta, and you have x and y, but you don't have the hypotenuse, then you simply do a tangent computation. Tangent of beta is equal to y over x. Of course, if you have y and x, then what you do is do beta equals tangent inverse of y over x. That is only if what you want to find is the angle beta. And beta is the one that is connected to the hypotenuse and therefore in the x value. So in this case, they rotated this triangular shape here, and x is from h to I, and y is from g to I. Okay, that means that what we have is indeed g to I over h to I. Okay, and we actually have those numbers already. So g to I is 5, and h to I is, we already had that number before, 533. 5.333. Okay, so beta is equal to 5 divided 5.33 tangent minus 1, and forget the parentheses, 43.2 or 43.17. Okay, and sure, they get 43.15, whatever, we're close enough. So with that angle, it's very simple, because if we do summation of forces in, we can do either x or y, because we have the angle now, right? Because this angle right here, that angle is beta. So FH, so this force is the cosine, and the opposite to the angle is the sine. So in this case, Fx is going to be sine. So don't be confused. It's just depending on how you find your angle. If you want to do cosine, then you can find this angle, which is 90 minus 43.17, but you decide which way to go. So if we do a summation of forces in x, it's not going to help us because, yeah, it's going to help us. We have F to H. But again, if we use a different method, we can make sure that computation is correct. So summation of moments at L is equal to 0, so that we can cancel out these forces, and we use the forces that are on the y-axis. Okay, so what does this mean? Let's do it again. Over here, summation of forces in L equal to 0. Let's consider the forces that we have. So first of all, we have this force here is counterclockwise, 1 times 5. It's not negative, it's positive. 1 kilonewton times 5 meters, plus 1 times 10. Okay, now all these forces are going to be cancelled, and we're going to have the force at B, which this is cancelled, but B cosine beta is not cancelled. So this force right here has a moment, which is also positive. F G to H times cosine of beta times 5, 10, 15 is equal to 0. Okay, now this force we don't consider because it's going, it's touching the point. Okay, so this force is not connected to the point, this force is not connected to the point, 7.5 is connected to the point, so we ignore F. The force from F to H is passing through the point, so this one is ignored. This one is passing to the point, ignored, and this one is passing to the point, ignored, but F G to H cosine of beta is not, so this one we consider. Alright, so it's just a matter of computing things. 5 kilonewtons per meter plus 10 kilonewtons per meter plus 15 F G to H cosine of 43.17 degrees is equal to 0. So this should be the same as saying Fg2H equals -5, -10, this is 15, yeah, and this is divided by 15 times cosine of 43.17 degrees. Okay, so we have 15 times cosine of 43.17 is 10.93. Well, that's not the whole solution. I apologize. That is what we divide as the denominator. So this is -15 over 10.93, which this is 10.83, okay. -15 divided 10.93, -137, -1.37 kilonewton. All right, so this is Fg2H. Perfect, so we have solved for Fg2H, which is only 1 kilonewton, 1.3, and is in compression, so that's good. We have solved for G2I, which is 13, which is in G2I is positive, and we have solved for F2H, which is negative. We have a negative sign here, and that is 14. Okay, so that is how you solve for the three forces that they asked us to compute.